So I want to start with saying a little bit about myself. I work in data science and machine learning, and I like to write software and solve data-driven problems. I'm one of the core developers of scikit-learn, as you might know, and I teach data science at Columbia. Recently, the Alfred P. Sloan Foundation has given me some money to work on scikit-learn while I sit at Columbia, and that's really amazing. So now I can spend more time on scikit-learn, which I always like doing. So just a little bit about what I do there. So you probably heard about this big fear that AI will take away people's jobs and we all will be out of work, and kind of does. If you have a job driving a car right now, maybe look for a different one. I think they'll all be automated in the not so far future. But I think it's kind of mean working on automating other people's jobs. So what I try to do is make my own job obsolete. So I want to make data science to become so easy that anybody can do it without having some machine learning expert help them. So they don't need me anymore and they can go lie on a beach somewhere. So, I mean, clearly there's some knowledge you need to do machine learning, to apply data analysis, to do statistics. So there's some certain bar, but I want to keep that bar as low as possible. And certainly I don't want people to need to know a lot about software engineering to do data analysis. So I think one of my goals and a shared goal of the scikit-learn project is to make machine learning as easy as possible and really allow practitioners from all kinds of areas in industry and science to easily use machine learning. And so yeah, that's sort of what I'm working on. Most of my talk will be about where AI is right now and its future potentials and pitfalls. And I also want to give my own point of view of what's happening in data science and where there's more hype and where there's cool stuff happening. And so as you can see, so maybe I should read my talk title. My talk title is Promises and Perils in Artificial Intelligence and Why You Shouldn't Trust Anyone That Uses the Phrase Artificial Intelligence. So I really don't like the phrase artificial intelligence. I'm going to talk about that too. So that's why I'm going to stop saying AI now, and I'm going to start saying machine learning, because machine learning actually means something. I also want to talk about current and future challenges in using machine learning in data analysis. And so everything in this talk was either done by someone else or it's not done yet. So none of this is my work. Because what I do usually most of the time is write unit test. And I don't know, if Nicolas is still here, I have to tell you, every time they pass, I punch the air, for sure. So yeah, I think the last 3 times that we did scikit-learn sprints like we did last week, I basically rewrote all the unit, or refactored all the unit tests. And yeah, you really don't want to hear about that. It's no fun. So, but let's get started about what's hope and hype in machine learning and data science. So I'm really actually an enthusiast, even though you might not notice. But so I'm really hopeful for machine learning and data science to make a big impact in many areas. But there's also a lot of hype out there and a lot of people trying to sell stuff. So people, yeah, make all kinds of claims because they want to sell their products, or newspapers make claims because they want to sell their articles. As I said, there's been a bunch of fear-mongering of like machine learning creating robotic overlords that will take over the earth or something. Luckily, that hasn't been there so much recently. But so what I want to do first is basically distinguish what is all the hype and what is like actually working. So I got to apologize to all the machine learning people in the audience. You'll learn nothing. So first, before I talk about this, I want to talk about some words that I'm going to use. So the first word I want to explain is data science, and the second is going to be machine learning. So I don't really like the term data science because, I mean, it's about data, but not that much about it. It's about science. But probably we're stuck with this word now, so I'm just going to explain what I mean by it. So usually data science is used as a very big umbrella term. And so what I think of data science is the practice of and the methods for reporting, inference, and decision-making based on data. And so you might argue that's very wide, and maybe it's just all of empirical science, or maybe it's all of statistics. Maybe that's true. So feel free to disagree with me, but that's sort of what I mean when I say data science. One important aspect here is that there's two sides. There's the practice of doing data analysis, and there's methods for. And so most people here are probably more programmers, so you're more working on methods. So methods for data science can be either doing databases or distributed systems, or can be creating new machine learning and new mathematical proofs. But so there's sort of people who work on methods, and there's people working on applications. And we saw a bunch of the applications over the last 2 days. And so everything basically deriving knowledge from data to me is data science. So this includes SQL queries, but it also includes counting. I really like counting. I think it's the most important data science technique. I'll come back to this. So the other thing I want to explain that you probably already know is machine learning. Sometimes people call machine learning artificial intelligence, and they make me really upset. So machine learning is a much narrower field than data science, and it's the area I mostly work in. It's also kind of hard to define, and so I'm not going to aim for a general definition, just sort of a useful one. In particular, I want to talk about supervised machine learning. So to me, supervised machine learning is extracting information from data to make predictions on new observations. So you have some data you collect, and you want to learn from that so you can make, in the future, you can make decisions automatically. And so I want to do a quick distinction of what is data science and what is machine learning to me. So I got this beautiful ad here on Facebook for a snorkel that allows you to breathe like a fish or something like that. And so data science questions associated with this are like, how many people clicked on this ad? So that's a good counting question. Or are men more likely to click on this ad than women? Also a good counting question. You could also do statistical inference about who's trying to clicking on this or not. Machine learning question is one where I want to predict something. For example, you want to predict for myself, like, will Andy click on this ad given his history of Facebook activity, my profile, and all my network, which is probably what Facebook's trying to do. And then some information about the ad. So you learn from who clicked on this ad beforehand, will Andy click on it? And so because Facebook showed me this, I guess their algorithm said yes, or at least sort of after going through all the auctioning that happens there and the trade-off for the pricing and the click-through prediction, they said yes. So I think we really shouldn't worry too much about robot overlords. Facebook has one of the best, arguably one of the best teams in AI. They have basically infinite resources, and they still think I'm going to click on this ad. And so we are safe for now. So one notion is really important and central to machine learning, which is generalization. So usually in machine learning, we collect some data from the past, and we want to try to make a prediction for the future. So in the ad example, it could be a history, as I said, of Facebook users that clicked or did not click when they were shown the ad. And then you want to make an inference for a new user. So here we collect data that happened basically in the past, and we make a prediction for what's going to happen in the future. Another common example for machine learning is that we're trying to automate a manual process. So you can think of, for example, collecting patient data together with medical diagnosis. So matter experts, so medical doctors, in this example, would give you a diagnosis for a patient. Now we can take this data, so the description of the patient and the medical diagnosis by the doctor, and try to automate this process, and thereby basically replacing or at least augmenting the doctor. So here, this was not data that was sort of naturally occurring to a process, but we collected data where there's some inputs, which is the patient data, and the output we want to predict. So that's sort of ML in a nutshell. And so the two cases for supervised learning is usually automating a process and generating and predicting the future. So now, more for the rant part, the other words I want to discuss, one is big data. So Wikipedia actually has a useful definition of big data. Let's see if I can read it. Big data is a term for data sets that are so large or complex that traditional data processing application software is inadequate to deal with them. So this is actually a useful definition, but I have issues with this term. First, this is sort of talking about volume of data, and volume of data doesn't really tell you anything about your problem. What's important is what does the data tell you, and how much information are you able to extract from this information. The second reason I don't like this term is it's abused ad absurdum. It's applied to basically all data. there are people who have a lot of data. So let's say traditional computing and data processing software is a laptop or maybe one big machine with Python on it. If you boot up a cloud instance, you get 512 megabytes of RAM easily. You can do a lot with that. So if that's traditional, going beyond that would be big data for me. But most businesses don't have more than like half a terabyte of data. And most scientists don't do that. If you're Facebook, okay, you need a cluster. If you work on the Sloan Digital Sky Survey and you have high-resolution images of the sky, you also need a big cluster. But most people don't need a big cluster. A lot of people have like 5 megabytes of data, and they set up a Hadoop cluster. Why? Or they have like a table with 1,000 rows or 10,000 rows and 100 columns, and Excel crashes, so they have big data. And this is really a disease you probably don't see that much in Python conferences, but you see all over in the industry. People, A, throwing around words and using too complex solutions. And so that's usually the people that use the word big data. So that's why I don't like that. And so there are big data applications that are very interesting, where there's a lot of data. But I don't think that's what most people do. And if so, and I don't think the people that do like the Sloan Digital Sky Survey that have like probably one of the biggest data sets in the world, I don't think they use the term big data. So I'm always skeptical if someone says this. Ooh, here's a fun example. Looking for data science definition, I found this one. I think it was the second hit on Google. And it says, defines data science as a subfield of big data. I got really upset about that. So it's not science or not data if it's not like petabyte scale or, yeah. So I don't trust Investopedia. Yeah, so the other term, as I said, that I don't like that much is artificial intelligence. So here's, again, this is a good definition from Wikipedia, which says, artificial intelligence is intelligence exhibited by machines. In computer science, the field of artificial intelligence defines itself as the study of intelligent agents. Any device that perceives its environment and takes actions that maximize its chance of success at some goal. Colloquially, the term artificial intelligence is applied when a machine mimics cognitive function that humans associate with other human minds, such as learning and problem solving. So this is a good definition, but it's way too general. It's like, this can be anything. So it's definitely more general than my definition of data science. Any program with an if clause can be claimed to behave intelligently. And a lot of companies do claim that. If they have an if clause, they're artificial intelligence. Because that means you react to input and you solve a problem. So right now, often when people say they use artificial intelligence, they actually mean they're using machine learning. But sometimes they mean they wrote an if clause. And I don't know which one it is, so that's why I don't like the term. Also, sort of colloquially, it means anything that kind of looks like a human. And so people use it when they have a human-like agent, even though it's completely non-intelligent. So you put in an avatar of a person or like a robotic whatever that just does a text search for you, which is basically how like Siri started out. And they call it artificial intelligence because it looks like a person. Yeah, so I don't really like that either. Sorry. So yeah, I said there's companies with AI in the title that do much less learning than what you do, what your phone does if you do take a picture. If you take a picture, your phone does image recognition to find all the faces, which I think is really cool machine learning. It's now like 15-year-old technology, but it's really cool machine learning. But I don't think anyone would call this artificial intelligence just because it's so commonplace now. But this is actual machine learning and not what people try to sell it as AI. So here, this is my quick summary of what I think what is hope and hype. And I talked a little bit about some of these words, but I'm going to talk a little bit more about some others. So basically, data science is any data analysis or any data analysis tools. So that's clearly useful. It's also nothing new. So it's a new name. Well, like, I don't know, how old is this name now? 3-4 years? But it's also, the techniques like statistics and data visualization and counting, they've been around for a long time. Maybe it's a useful umbrella, and so, but like, I don't know. There's no reason to hype it up again, but I mean, there are some useful tools. The tools themselves, like, as I said, data visualization, counting, and statistics, and machine learning, they don't get this much hype, even though they are really the technologies that are used. One part of ML that gets a lot of hype is deep learning. Oh, who here knows about deep learning? Ooh, okay. So I was told this is a Python audience, not a machine learning audience. Otherwise, I would have given another different talk. But so, okay, you all use deep learning. And deep learning, there's definitely a lot of hype. For a good reason, deep learning works pretty well in a lot of fields, but it's not really a cure-all. So yeah, I don't know. It's kind of cool, though. Yeah, and so as I said, words I don't like are big data, AI, and I also don't like bots, because bots pretend to be humans, even though we can't create anything that behaves like a human at all. Deep learning's cool for things like computer vision, audio, and speech. I want to talk a little bit about that, but it's also very cool for making your selfies look like they're painted by Miro, which is what I did earlier. So this is kind of fun. But yeah, so now I actually want to talk about the cool data science and machine learning techniques and where we are and what we can do right now. So as many of you do machine learning, you probably all have your own applications, but just wanted to give an overview of what's happening. So, I want to go back and basically look at how machine learning applications are done right now. So the task that I think is most easy to understand is classification. And it's also one of the most useful ones. So let's say I have a picture of a snake. I like snakes. And I want to know whether the guy in the picture is a ball snake or a carpet python. As I said earlier, to build a machine learning model, so we need to collect a bunch of data, so we know what's the right answer. So I'll collect a bunch of images for which I know they're a ball snake and for which I know they're a carpet python. So here I put 4 each, but more realistically, you'd have to couple of thousands. You collect this data, and you can build a pretty good classifier to distinguish these two kinds of Python. And I think that's pretty impressive. So that's only been true for about, let's say, 6 years. So but I feel like thousands seems like a lot of images. And the problem is that each time a machine learning algorithm starts to learn something, it basically starts from scratch. Anytime we solve a new task, we basically start with a newborn baby that knows nothing about the world, and it doesn't even know how its own eyes work. So if we start with literally zero knowledge, we need much more data than if I would try to teach you how to distinguish these two snakes. You already know perspective, you know how colors work, you even know what a snake is. So it's much easier to tell you this than something that doesn't know anything about the world or anything about vision. So one way in which deep learning improved over this is that people build models that are generic enough that they learn about seeing so that we don't need to start from scratch every time. So you start with a model that was trained on a huge number of tasks, and now we can start learning new concepts much more easily, say using hundreds of images instead of thousands of images. So that was a pretty big breakthrough in the last 3 or 4 years, enabled by deep learning. So now you can use these ready-made models off the shelf, for example, by just using pip install keras, and then you can load a model, and you can use this to build any new classifier for visual concepts. But this is still not how humans learn. You still need hundreds of examples, even with these pre-trained models, and the models don't know anything about scale or rotation or perspective or anything that's important for what's happening in the world. It's like taking a newborn baby and flipping hundreds of photographs in front of their face and telling them what they are, instead of the baby interacting with the world. So people build similar generic models for audio and text processing that also allow you to sort of bootstrap your learning process. But all in all, this learning is very different from how humans do this. However, one thing that's great about machine learning algorithms is that they're very, very patient. And they're relatively fast. So they can look at a lot of data. So maybe you can learn to distinguish these two kinds of snakes from 10 pictures. And the computer needs maybe 10,000 pictures or 1,000 pictures. But if you show the computer 100 million pictures, and these are the right pictures, then the computer will be much, much better than you are. And there's no way I'm going to show any of you 1 million pictures. You're going to like fall asleep. But so the computer might be able to be much, much better at a very narrowly defined task if you give it enough data. So this is really great. And so basically, we can automate all tasks that are very repetitive and very well defined. But this only works if I do this for these two kinds of snakes and only in the setting that I trained it for. The model would still not know anything about this being animals or that the world is 3D or really anything. But you could be perfect in this very narrow task. So one example I like to give you where this is useful is medical imaging. So for example, there's a lot of people trying to find cancer in medical images, and it's a very hard task. It requires expert trainings, and doctors are very expensive. So it helps if you have a computer that can assist with diagnosis. But they can not only augment the doctors. The thing with the diagnosis system is that each doctor will only see so many tumor images in their lifetime. So even if they're experts, and even if they know a lot about the human body and about the cancer, they can maybe only look at like a couple hundred or a couple thousand pictures in their lifetime and learn about these. A computer might be able to look at 10,000 or 100,000 times more images than they are. And so if you have the right data and the right specifically defined task, you can become much, much better than any human expert. And so this is true basically for all simple yes-no questions in a well-defined domain, like sick or healthy, or what kind of snake. You can also do this if you have more classes. Researchers did stuff for like 10,000 classes of different visual objects, and that works reasonably well. And so that's pretty impressive. If you can get enough data, you can train superhuman models. So to summarize, so machine learning generally, they need to start from scratch, though we're kind of working around this, but only very like rudimentary. And but still, the algorithms need a lot more data than humans. If we give it enough data, then they can become better, but only very narrowly defined task. And the problem why these tasks need to be so narrow is, among other things, that algorithms have no way to interact with the world. Many researchers think that it's a requirement for building rich representation or a mental model of what's happening in the world is that you can interact with it. But computers are usually just static and are shown some data from the outside. However, because you can potentially give a computer much more data than any human, they can become better on this narrow defined task. However, there's like other tasks that computers are not very good at yet. So 10,000 possible classes might sound impressive, but if you look at other applications like question answering, there's much more possibilities than 10,000. Writing an English sentence is much more than 10,000 different outcomes. And so machine learning is used to generate text in many applications, like looking at Google Translate, for example, which is pretty impressive, but it's nowhere near where humans are. So there's still a lot of work to get to superhuman level there. So whenever you want a structured output like speech or text or anything like that, computers are still far behind, and we don't really have a good way to solve this yet. There are some examples where generating text is easy, and people sell this as AI. So for example, text generation is used a lot right now in newspaper articles on sports and for business reporting. And that's great AI because it's very easy to write articles about sports because they're very boring. So basically people have templates. Player X scored for team Y in minute Z. Team A won by B points. Or the quarterly earnings went up by X. The stock went up by Y. Production went up by Z. And people actually generated these templates and used them to automatically generate articles that are sold and read by people. And so you don't really need any machine learning for that. It's just text replacement, but that at least works, but it's not very interesting. So generally, predicting structure is really hard. And another set of problems that machine can't really solve is those that require knowledge about the world. So you could also make a question answering machine that just says yes and no, and it would just be a binary question. But if you require knowledge about the world, machine learning algorithms can't usually solve problems. We use an amazing amount of knowledge of the world and how everything works without even noticing it. So if you take the snake classifier, it doesn't know that there's a 3D world, for example. So if you show it a picture of a hand holding a photo, it'll say, this is a snake, and tell me which snake it is. But it has no way to distinguish the concept of there being a photo and not really it being a snake, because it hasn't learned about photography or hands or anything. So as this is not part of the task, unless you explicitly train the model to detect hands, you're not able to figure that out. So generally, this prevents algorithms from solving any task that involves inference or knowledge about real-world objects. Often objects are defined by a function, not by their appearance, and as long as you don't have a way for the algorithms to interact with the world, we can't really solve this. So you can't resolve anything that relies on functions or context. And I'm not aware of any system that actually solves this in any way. So anyone who's doing AI, or claiming they're doing AI, none of them are able to handle any knowledge of the world, really. There's this picture that people in computer vision conferences always like to show. I don't know if you've seen this. So probably everybody here gets what's happening. So there's this guy, is weighing himself, Obama puts his foot on the scale, and everybody around laughs. So no machine learning in the world can understand this. And I don't think any machine learning in the world will be able to understand this in the near future. So if you have a good algorithm, you can count the number of people, you can give maybe their gender, their facial expression, you can maybe find like the stick figures of where all their limbs are. Maybe you can even find a scale, but you can't understand what's happening because there's no machine learning algorithm or computer vision algorithm that knows how a scale works. So you would need to know that putting the foot on the scale changes the outcome. You would also need to know that the guy on the scale can't see Obama, and you would need to know that the smiling is because the people can see it. And I don't think there's any researcher that even has any idea how to start on this. Well, maybe start, but there's like nothing that works like this. So that's why I'm also skeptical of people claiming they use AI. So summarize what a little bit where we are today. So if you have many examples, you basically can classify simple things in a narrow-defined task. And this works in the real world, and it often can become superhuman. Like for image recognition, we have many algorithms that are superhuman now, as long as you don't need to interpret the picture. So generalizing to new concepts using few examples is something that works in papers, but rarely works in the real world. Similarly, producing text or complex objects is something like there's Google Translate, but you don't want to write a book using Google Translate. And so reasoning about real-world knowledge and what objects do in the world, I don't think anyone has an idea. So, okay, this was sort of where we are right now. So now I want to talk about some specific challenges in machine learning that arise and that I think are really interesting. And they're not only part of machine learning, but they're also part of counting and statistics and anything that's related to data-driven inference. So one of them that already came up this morning is understandability and interpretability. So this is one of the biggest issues people have with using machine learning in practice, is they want to understand how the algorithm works and why a particular decision was made. This is not something that a lot of people in the machine learning community think about, but it's something that's very fundamental to most applications. The problem is, the more powerful an algorithm, the more complex it is, and the less open to interpretation. Any algorithm that's powerful enough to categorize images will be very hard to introspect or understand. So for some applications, it's okay to have a black box that provides answers that are usually okay. For other applications, it's really crucial that you know why a decision was made. If Facebook suggests to tag your wrong friend in a picture, it's not so bad. But if Tesla misses a pedestrian in front of your car, maybe you want to know why it happened, so you want to fix the problem. With most current algorithms, it's not possible. So the things that we want to know often is what did the algorithm learn, and why does it make a particular prediction? For example, if a loan is granted, or maybe if a bail decision was made. Both the financial system and the criminal justice system in the US make wide use of machine learning, but often without the ability to understand why a particular decision was made. That means people end up in prison, and the reason they get is the machine said so. That's not great. On the other hand, there's a lot of regulations in the financial areas which require that you're very strictly can explain models, which means that you cannot use any powerful models at all. So for example, in credit scoring, they're all used like very simple linear models because otherwise the regulation will not allow them. That means that basically use simplistic models, you make bad prediction because there's too much understandability that it's required. So apart from the application, it's also really important for people that work on machine learning methods to understand what's happening, because right now we don't have a debugger. If a model doesn't work, there's basically no way for us to figure out why it doesn't work. And so that's kind of tricky. So as I said, the most powerful models are hard to understand, hard to interpret, but that's actually true for most models. So for all models, you can always write down a formula why a model made a decision, but usually this is completely useless. So for a linear model, it might help, but if you have even a random forest, there's no way that any human can interpret what's happening. Finding out what a model has learned or why it has learned it is even harder. Even if you have a linear model, you have no idea why the coefficients are the way they are. If you like remove or add a data point, everything might change and you don't really know why. So I mean, people are working on this, but right now most machine learning is a black box in one way or the other. Counting doesn't have this problem as much. So counting works. That's good. The other problem that most applications have is bias. And that also applies to counting. And it's closely related to interpretability. But it's actually, even if you can interpret a model, it might still be biased. So again, if you're making life-changing decisions for people based on algorithms, we better make sure they're not biased. We all have our more or less conscious biases. And ideally, we'd like to have a machine that gets rid of the biases that we have. However, machines are usually trained with past data. So machines learn the societal biases that we have and that created the data. So here's an example that was featured like a year or two ago by ProPublica on bias in the US justice system in assessing the risk of whether someone will offend again. So here, the idea is to decide whether you will allow someone to post bail so they don't need to stay in prison based on their past. And you can see these two things. There's the person with 2 armed robberies and 1 attempted armed robbery and 1 grand theft. And you might not be able to see this, but this is a white guy. And then on the right-hand side, you see someone that has 4 juvenile misdemeanors, so basically maybe smoked pot sometime. And so you can see that the person who likes to do armed robberies and grand theft is very low risk, and the person that did something in their teenage years is high risk because they're black. And so this is a system that's in production right now and used. And so one of the biggest problems here is maybe not that it's biased. Okay, that's a big problem. The other problem with this is that this is a proprietary algorithm, so the public is not allowed to see the data or see the algorithm or see the decision-making process, but even the justice system doesn't know what algorithm is used or how any decision is made. So that's great. So actually, and if you look at their specification, the definition of fairness that they use to predict the probability of recidivism, so if someone offends again, is given the score that they produce of low risk, high risk, whatever, given that score, the probability to offend again is independent of race, which means that the score should be maximally racially discriminative. That's what the definition of fairness says. So there's a lot of problems there. And so fortunately, there's a lot of cool people working on this. There's this whole conference, not sure if you heard about it, Fairness, Accountability, and Transparency Machine Learning, or FATML. And so this is basically all about bias and understandability. And you should go there, check out the papers of the recent years. You should go to this conference this year. I think it's co-located with AI Stats, but I'm not sure. Yeah, so fairness is another big issue. The last issue I want to talk about is privacy, which is also an issue from counting to statistics and machine learning. Basically, by aggregating and learning from data, companies can learn an incredible amount about everybody, which might think is concerning. On the other hand, if you're working on medical applications, the privacy concerns can mean that there's no data to actually build models from, which means there's less models to save lives. So we need to strike a balance between protecting individual data and building powerful models. And there's some interesting problems like some interesting approaches like differential privacy and learning from encrypted data, and that allow creating models without actually sharing data. And so this is still not really solved and not in scikit-learn yet, also not in scikit-learn contrib yet, maybe soon. But that's also something that I feel like we're still struggling with a lot. Oh, so I have 3 more minutes. So I wanted to add some optimism because even though I like to criticize everything all the time, I'm really optimistic. So I think ML can already do a lot of amazing things. And if you're not using ML in your company or your research, you're probably missing out. And so for all of these problems that I talked about, there's already a lot of work, and there's even more work to be done. So I like this because it means I can keep on coding and doing Python stuff instead of lying on the beach, which is kind of boring. So the last thing I want to talk about is where Python and scikit-learn fits into this. So far, I've talked only about like data science and machine learning in general, and I haven't really talked about tools. So I left Gail talk about tools in the talk before this. So I think Python is playing an incredibly important role in this area, in particular because it provides free and accessible tools. And they're easy to use. So you have NumPy, SciPy, Matplotlib, Pandas, scikit-learn, and Jupyter, and many other tools. But there's like certain core of tools that really provide a common infrastructure that we can all use. There's also Keras, which I love. So Keras, if you don't know, it's a library for deep learning. It makes it really easy to work with text data, audio data, image data, and yeah, provides incredibly powerful tools that are easy to use. One thing that is true about all of these, though, is that they all are focused on in-RAM computations on a single machine. So far, PyData hasn't focused so much on the big data thing. There are some other tools for distributed computing. There was a talk today about how you can use joblib in a cluster setting. You can use Dask. You can use Spark interfaces like PySpark. But what I really think is that we should not spend all our effort on trying to distribute everything because most of us don't have big data. So there's definitely interesting big data use cases, but for me, I want to work on the tools that we already have and work on in-memory problems because there's so much more we can do. So it would be nice if you could scale out a little bit more smoothly and not replace your whole stack once your data becomes bigger than RAM. But first, I'd like to really solve sort of the simple use case and yeah, don't focus on clusters too much. Okay, so I mentioned some projects that I think are core. And so, like NumPy, SciPy, Matplotlib, Pandas, and scikit-learn. And obviously, there's many more packages. But as I said, what I think is really important about the ecosystem here is that we have these core libraries that create a common language that we can all rely on. I used to work in C++ a couple of years ago and do machine learning in C++. If you started a new machine learning project in C++, the first thing you needed to do is you pick an array library. The second thing is you write all your I/O from scratch. The third thing is you pick a GUI framework. And you have now thousands of lines of code, and you haven't done anything. In the PyData community, we have settled mostly on the interfaces, on the data structures, and we have a battery of algorithms that we can all use. And so I think this is the real value in all these packages, is that they create this common shared language. So this really reduces a lot the friction of any new project or for any new collaboration. So I think that's all that I had. I wanted to mention one more thing, and which is you should buy my book. It's about machine learning. It's written for programmers. Okay, all of you know machine learning, so maybe it's not for you. So this should be easy to read if you know any NumPy. I avoided putting any math in it, so there's no formulas. If you want math, there's great math books out there like Elements of Statistical Learning. This one is like how you get started with machine learning in Python, which is why it has this title. It also serves as a guide on how to use scikit-learn. All right, so that's it. I hope my rant was a little bit informative, and thanks again to the organizers.